Hi, I'm back here with another video. This is the question number 4 for JEE Advanced 2023. As we have been doing in our previous videos, the very much detailed discussion of the questions which were asked in JEE 2023. We have done 3 questions from paper 1. Now we are on to the 4th question. This question is from section number 2. This question was based on qualitative analysis. So this was having only one option correct question, that was from section number 2, and marking scheme as per this section was +3, -1 and 0. Here's the question. They asked in the scheme given below, X and Y are to be identified, and please note this is not about P and Q, this is about X and Y, which are going to be the final products in this reaction sequence. So they had given over here, we had to find X and Y, and the compounds which are being produced when this metal halide is being reacted with NaOH, we are having this white precipitate P and the filtrate Q, and then this P and Q, the precipitate and the filtrate, are being reacted with this group of reagents so that we are getting X and Y. And then they are asking about the properties of X and Y, like X is giving a colored species in solution and Y is something which is giving blue coloration with the KI-Starch paper. And then on that basis we had to identify which one of these is X and which one of these is Y. Okay. And the reagents over here which were given to us, they were the aqueous H2SO4, this precipitate, white precipitate, what is being produced, that is being reacted with aqueous H2SO4. The reason would be that precipitates are usually, a number of times, not usually, they can be dissolved in acids. So that white precipitate, which is expected to be basic in nature, can be dissolved in acidic compound, provided that that compound is not going to be, that sulfate of that compound is not going to be insoluble. For example, barium and lead, those kind of compounds will not be dissolving in aqueous H2SO4 if it is diluted. And then when that precipitate is being dissolved, then this is being reacted with PbO2. Now this is a little bit tricky. If you have seen the reactions involved in the qualitative analysis, then you may have an idea how PbO2 behaves. Otherwise, in electrochemistry, when we do lead storage batteries, if you ever have been paying attention, you could have realized that the SRP value of this PbO2, when this is converting into Pb, that is lead 2 plus, as having very high positive SRP value. We'll be seeing that in a moment. So this is basically very strong oxidizing agent, and this can be one among the top 10 oxidizing agents after fluorine, which can be available out there and throughout all the chemicals known to us. So then when we are having PbO2 oxidizing that white precipitate, whatever metal basically we would have expected over here, that may possibly be oxidized, and that can be giving us the colored solution. The colored species can be present in the solution. Okay, moving forward, we have got the reactions of Q. So the thing which was not forming precipitate, which was moving on to the solution, that is reacted with MnO4 twice. Manganese over here is in +4 oxidation state, and sometimes that MnO2 dot H2O is considered to be MnO4 OH twice. So basically manganese in these compounds is going to be in +4 oxidation state, whether you write MnO2 or you write MnOOH twice. That's basically hydrated manganese dioxide, we can believe. That is again the oxidizing agent, but its oxidizing ability is relatively less in comparison to the oxidizing ability of the lead dioxide or KMnO4 or K2Cr2O7. So when we are considering this reaction sequence, Q is being further oxidized by these things in presence of heat, and then we are getting some Y as the final product, which is known to give us blue coloration with Ki and starch paper. This is a very important reaction in iodometry and iodometric iterations we might have seen, where any oxidizing agent which can oxidize iodide into I2 is known to form some Starch-iodo complex, which is known to have this kind of blue coloration. Sometimes we say bluish black color or dark blue coloration, depending upon the references we can be using those different terms. So now if you have to select for X and Y, you have to see the possibilities, like what are the possible compounds and how that precipitate which is being formed is being reacted further, and what can be the possible reaction. Although the options were given in a way, you could possibly eliminate the rest of the option quite easily if you pay a little attention. Anyway, we are going to do detailed discussion, so we'll be pinpointing every single discussion which could be possible in this question. So if you don't look at the options, just see what the question is telling us about, then what would be our thought process. For the white precipitate of the metal over here, there are many possibilities present. Like many of the metal hydroxides, and this is very much obvious that if you are reacting with sodium hydroxide, then this is possibly going to be some metal hydroxides precipitate. Although some other possibilities could also have been there, we can rule out those possibilities in a moment. So for metal hydroxides, there are many precipitates known, but out of all those possible precipitates, whether all of these are white, that is not necessarily. Like many of those precipitates are there, but they are not white. And among those which are white, they also should not be possibly soluble. So we'll look at the clues first. We'll see what all information was given to us about this compound number P, and then we'll proceed further. So this is giving precipitate, that is understood that the precipitate P is not going to dissolve in sodium hydroxide, because if it is dissolving, then P will no longer survive. This will convert into that kind of soluble thing, whatever could be possible. So first thing, P is white. Second thing, this is not dissolving in sodium hydroxide. That is enough clue which can be helping us zero in into one particular option. So few more clues we were given about this precipitate P. One thing was in the next reaction sequence, if you see, this was told that this is soluble in H2SO4. And in fact, why we are putting H2SO4 before adding PbO2? Because we want that our precipitate should be easily available in reaction medium, and then when we are reacting with this oxidizing agent, this can be very easily oxidized. So we want to make it soluble. Although it was not very specifically told in the question, but we are kind of making an inference from that why we are dissolving. What is the use of sulfuric acid? Another possible reason could be that lead dioxide, PbO2, which we are using over here, that PbO2 would be requiring some acidic medium where it can be easily reacting. And the information which was over here supposed to be understood, basically information given was supposed to be interpreted in a way that hydroxide precipitate is dissolving in sulfuric acid and that is being oxidized. That was the one information. Another clue which we could see coming from the given information was that our precipitate is getting oxidized. This is important point. We'll be ruling out the number of further possibility possibilities which cannot give us this kind of oxidation possible. And also there was one important clue that in the product it was known that this is giving us some colored species in the solution. This was also told that oxidation of the P is producing some compound which is colored in nature. Okay. Now here we are having the different colored solutions, basically the colored hydroxide which are being precipitated. So we will be seeing here which of all these compounds can be white and which of these can possibly be our compound number P and which cannot be. We can rule out the rest of the options. So white of all these metal hydroxides which we have known, and actually we have tried writing these hydroxides as per their blocks, although not as per the groups as well. We could have possibly done that as well. So left two are coming from the S block elements, and over here they are all coming from the D block elements, and the last two are coming from the P block. So these different hydroxides which we know are undergoing precipitation as hydroxides, they some of these are white. So which one are white is calcium onto the left, magnesium second one, and other than that we are having manganese as well, although this we are considering is going to be very light pink. In fact, we can consider this as white if this concentration is quite low. That can be giving us white coloration as well. And other than that, we are having those onto the last three, that is zinc and then lead and then aluminium. So these 6 are the only which we can consider as white. The rest all which we see over here are going to be the colored, starting from this copper hydroxide up to this iron, cobalt, and this up to zinc. Before zinc, all these compounds are going to be having some or the other color. Manganese in the between is having only that different situation, which we can consider as very light pink or white depending upon the references. Okay, moving on, we are having here now the discussion about which cannot be P or which can be P. So our thought is that the first two cannot be P because these two compounds cannot be oxidized further. We are saying that compound number P, which was obtained as white precipitate, is being oxidized further to give some colored compound in presence of sulfuric acid. So some colored compound cannot be coming. In fact, calcium and magnesium cannot be oxidized further and they are not known to give any colored solution. So we can rule out our white precipitate cannot be magnesium or calcium. This is not the case. Okay, and the reason we are not taking beryllium over here, beryllium could also have actually given the precipitate in the beginning, but we know this beryllium is also amphoteric in nature, and we know this is dissolving in, this is soluble in sodium hydroxide, and that forms sodium berylate Na2BeO2, which is soluble in water. So beryllium also would have not been there because, and in fact, if there was not an option which was having beryllium and all, this is just for the sake of reference. When we are looking the reactions, we can be thinking of solubility in sodium hydroxide as well. Moving further, we are having our discussion about why it cannot be the last three options, which were your zinc, lead, and aluminium. So because these last three which we are seeing over here, which are appearing white in color, but they cannot be because they are all soluble on sodium hydroxide, and we know when they are dissolving, we are forming, the first one is forming sodium zincate Na2ZnO2, which is soluble in water, and the lead one is forming sodium plumbite or plumbate depending upon the conditions. So Na2PbO2 can be sodium plumbite, which is going to be soluble in water, and aluminium is known to form sodium meta-aluminate NaAlO2, which is also soluble in water. We can have sodium orthoaluminate as well depending upon the concentration of the hydroxide ions in the solution, right? Now we are saying the precipitate of these all amphoteric metals, they can only be generated if you are using ammonium hydroxide. Reason being, ammonium hydroxide is going to have relatively lower hydroxide and concentrations, so it does not provide very high concentration which can be required for dissolution of these metal hydroxides, which is done in the presence of sodium hydroxide. So ammonium hydroxide, being weak base, will keep lower hydroxide and concentration, and that lower hydroxide and concentration can keep all these things soluble. Although we are saying in this case, when the precipitate of these things is required to be generated, out of these three options available, zinc hydroxide is known to be soluble in the ammonia or ammonium hydroxide as well. And the reason is this will be forming some complex, as we are seeing for the case with the number of other transition elements, or in fact D block elements. Zinc we sometimes refuse to believe as the transition element. This kind of complex is being formed with the zinc, which is soluble in water. So zinc hydroxide will be soluble in sodium hydroxide as well as ammonium hydroxide. Lead and aluminium, they will not be forming any soluble species if you are keeping the excess of the ammonia. And actually, not just ammonium hydroxide or ammonia, the zinc hydroxide is also known to be soluble in number of different ammonium salts like ammonium chloride. If you put ammonium chloride, because that can be generating enough ammonium ions in the solutions which can be converting into ammonia, and that it can be forming the complex, and it can be getting solvated. It can be dissolved in the aqueous medium. Moving further, we'll be talking about now the manganese hydroxide, MnO2. This MnO2 we know is going to be almost white in color, and this is insoluble in sodium hydroxide. And why insoluble, we'll be talking of in a bit. We are understanding this can be oxidized further as well, so this is going to be the potential candidate. In acidic medium, this can be converting from manganese +2 over to manganese +7, which is basically appearing as MnO4 minus in the solution. And this is again, we are emphasizing that although manganese 2 plus ions are sometimes considered to be colorless, but they are actually very, very light pink. So their precipitates also can be considered the same way. If it was colorless, we can consider that precipitate is going to be white. If it is very light pink, then the precipitate can be having some pinkish tinge, as you can see over here. This is not exactly white. This can be deemed to be white. We can go by the philosophy of JEE, and we can believe, or better we say we have to believe, they were talking about the manganese only, because all other options can be ruled out very easily. Yeah, one more point was left here in the previous discussion. We were saying that manganese, that MnO is very, very basic in nature. Although if you talk about manganese dioxide or even Mn2O3, they are amphoteric in nature. MnO2 very clearly amphoteric, Mn2O3 up to a certain extent this is amphoteric, less amphoteric than MnO2 you can say, or you can say MnO2 is kind of more towards basic side, less towards amphoteric side. But it is amphoteric because it is known to dissolve in the acids as well as bases if you keep the concentration of bases quite higher. And then MnO, there is no confusion saying this is clearly basic, because it does not dissolve in the sodium hydroxide, and that is why we are getting here the precipitate in this particular question. Also, we know that chromium CrO2O3, which is converting into chromic hydroxide over here, this one. This is also known to be amphoteric. That can also be like if this is converting into say CrOH thrice, that can also be converting into precipitate, but that precipitate is not white. That is going to be green in color, as you can see over here in this particular test tube. Okay. That is green color, which is coming from the precipitation of the CrOH thrice. If you are putting sodium hydroxide, it will be dissolving further, although it is amphoteric, so it will be dissolving. If you would have put ammonium hydroxide in the solution of chromium salts, it would have given us green precipitate and not the white, as it was asked in the question. Moving forward, we are having here the discussion of what it could have been or what it possibly could not have been. So that Q, which we have seen in the beginning, It may actually be any of the cation or anion, cations like sodium or anions like chloride. If we don't know any of if we are not looking at the options, we can be thinking in all the possibilities. It turns out that because the sodium and chloride, they are having most of their salts soluble in water, so this could have been passing into the precipitate. But later, if you see the reaction sequence, what was happening, that the Q is getting oxidized by manganese in acidic medium. That is the last reaction sequence over here. So we know that sodium, iron, potassium, or any such S block elements which are very much soluble in water, they cannot be the part of filtrate. This has to be some anion in particular, because those anions can possibly be oxidized by the strong oxidizing agent. We are saying filtrate Q cannot be any of the S block metal ion. It may be some soluble chloride ion or bromide ion or any such anion which can be very easily oxidized by the MnOH twice or manganese plus 4. So that was one idea about how we can think about Q versus P. Now, if you try to eliminate the options, because we are not going to have very clear answer, we can try to see the reactions, and the reactions of anions may be looking like, it may appear that if you try to see the options, we were having bromine, chlorine, chlorine, and HOCl. It appears we should be thinking either about the chloride or about the bromide. So either of chloride or bromide can be possibly the answer. We cannot eliminate the options A, B, C, D just on the basis of Q. We have to look back at the option number, like the compound number P as well, then only we can rule out possibly. So because if you're thinking of Q, which may be either chloride or bromide, each of this chloride or bromide will be oxidized into chlorine or bromine by this manganese plus 4. That oxidation is going to happen in presence of manganese plus 4. So, and it is also known that both the chlorine and bromine, which are further, it is given that KI-Starch paper is turned blue, both the chlorine and bromine can do so very, very well. And that starch, that blue coloration, what is supposed to be coming in this final step, that is supposed to be coming from some starch iodine, starch-iodo complex, we should say. Sometimes we are saying iodine-amylose complex, starch-iodine complex it is supposed to be. So that starch-iodo complex looks like this. These are your iodine atoms, and in fact this is not just iodine, this is what we have represented over here. This is triiodide iodine and I minus complex, you can say, which is looking like this. And this helix kind of thing, what is coming, this is coming from starch, and in starch we are having two things. One is amylose and one is amylopectin. We are talking about amylose over here. Starch is also containing some amylopectin as well. This blue coloration is found by the amylose part of the starch. Here we'll look a little deeper into this, how starch amylose complex looks like. Actually, the iodine amylose complex, we should say better. So the molecular iodine is going to be converting into like the Ki, which we have taken in the beginning, potassium iodide. This will be undergoing oxidation. Whatever oxidizing agent we are taking, that can be converting this into I2, and then this I2 can be combining with the iodide, and that can be generating I3 minus ion. That is what we have tried representing over here. And this is not just that reaction stops at I3 minus ion. There are evidences that I3 minus ion can be combining further with the I2, and there can be formation of I5 minus or things like that. The situation is that we are having many such polyiodo complexes known. So this kind of complexes can be generated. And now coming to the point, triiodide, which is I3 minus ion, is going to be very, very big. And also this is going to be electron rich. That is fine. But iodine is not very much able to hold its electron density very much easily. So there are going to be huge dipole interactions possible with this triiodide ions and the hydroxyl groups of the glucose units which are present in the molecules of starch, actually amylose. And those interactions we can see over here in this diagram, where this is a trail, this is end on view of this starch amylose, this iodine amylose complex. This is end on view. So these are all the lined up iodine molecules as triiodide ion, and if you see all the hydroxides coming from all the around, this is the hydrogen atoms. The white are the hydrogen atoms and black were the carbon atoms, and there would have been some oxygen atoms as well. So the interactions which is going to be here, this all iodine atoms can be attracting all the OH groups, or the in fact the CH groups also up to a certain extent. They can be attracted to this very strongly. So here from we can say there can be very strong dipole-dipole interactions possible with this iodide which is present in the center, and that helix of the amylose complex which is possibly there. Moving further, how this amylose looks like if you talk about the amylose, which was the part of the sugar. This is basically, we say, the linear polymer of the alpha D glucose that we have seen in the biochemistry of the carbohydrates. And because there are many of the OH groups present, at least 4 OH groups per unit of the alpha D glucose are left in the amylose. 4 OH groups are free per glucose unit in amylose. All these 4 OH groups can be helping it get coiled over itself, and this can be forming helix by folding over itself, as we can see in the diagram over here. And these are basically, we call that 1,4 glycosidic bonds, and those coiling over of these different glucose units can be giving us one situation that along this helix, along the, you can say, the cylindrical axis of this helix, there can be some molecules trapped. Different molecules, depending upon their interactions, depending on their size, they can be trapped inside. And this is actually what we are doing, similar to this we are doing in the form of that medicines and drug designs, when we are using cyclodextrins in something called as sustained release. There are a number of medicines which are having this term SR, which is sustained release, which is when we are making such kind of cyclic structures around some drug molecule, then these bonds which are present in the alpha D 1,4 glucosidic 1,4 alpha D glucosidic bonds which are present, they take some time to get hydrolyzed. So those medicines which are administered enclosed inside cyclodextrins, it takes some time to get those medicines released in the bloodstream. So they can be having relatively longer lasting effects. Like if you are using those medicines in as it is in their usual form, as we consume those medicines, they can be going inside, they can be digested and going to the bloodstream instantaneously, or whatever the time frame is, say 2 hours or 3 hours, they can be going to the bloodstream. But suppose we want, after taking medicine just once, it has its effect, say up to 8 hours or up to 10 hours. We cannot do that with the traditional medicines. There we are using such kind of helical structures. We call those molecules as cyclodextrins. Depending on the number of the glucose units put together, there will be one kind of ring size, cavity size, and the medicines which can be having suitable size, they can be incorporated over there. That is what is the use of these OH groups which are present. They can be forming helix, they can be forming one kind of circular structure as well, in which the medicines can be encapsulated. So just like cyclodextrins which are used for medicines, here we are seeing the triiodide ion is incorporated inside this helix, and that is how amylose iodine complex looks like, which we can see once again in this diagram. So what was happening in this diagram, that in this image, amylose is coiling around triiodide ion. In this diagram, actually, in this image, what I have taken from this website, we are having, they have shown that there's a triiodide ion present. But there are chances there can be other species like I5, I7, I9. They can also be present inside the helix, which are responsible for the bluish black coloration. And the calculations from DFT and all suggest that it is not just I3 which we are seeing in this image. This is I3 unit over here. Maybe I should use a different colored marker so that you can see it. This one is one triiodide which they have shown in this image. There are evidences that is not just I3. there are I5 minus, I7, I9 minus, and those kind of species are also present. And I5 minus is, as per calculations from DFT, is going to be the major reason which is going to give us this bluish black coloration or the deep blue coloration of the starch-iodo complex or iodine-amylose complex. Okay, and we are talking about this DFT, which is basically density functional theory. That is coming from the that is basically the theory which is coming from the quantum mechanical method, which we are using in physics and chemistry to calculate the electronic structures, their energy levels and all for the different cases. For solids also we have used that. And this is the discussion coming from this paper from the molecules, which suggests that it is not just the iodine molecule. There are a number of different species present as well, which are responsible for the color of these different of this starch-amylose complex. And they say the color is arising, that color is basically coming from the absorption, this particular frequency, or we should say this is wavelength. This color is coming from the charge transfer band, and which is coming from the transfer of electrons from the HOMO orbital of this polyhalide. And this is not necessarily I3 minus n over here. They suggest in this paper that this is possibly I5 minus, like the chances are, the major evidences they say is that this is coming from the I5 minus n. So HOMO orbitals electron are going into I2 iodine's LUMO orbital, and that is going to appear as the charge transfer band at this particular wavelength. That is the reason coming from the DFT theory. DFT is this one we have called as the density functional theory, and that is used for the different quantum calculations to get different answers. Moving further, we are going back to the reactions of the anion. So what reactions we have seen as of now? It was that on the basis of Q, we can actually not distinguish anything. No option can be ruled out. And manganese is although known not to oxidize chlorine into HOCl, but this is possible that HOCl can be formed. So option number, like none of the options, neither this we can rule out, because HOCl can also be generated. Although manganese dioxide cannot oxidize chlorine into HOCl, but when manganese dioxide is oxidizing chloride into chlorine, then that chlorine what is being formed, it can undergo acidic hydrolysis. We are saying not acidic hydrolysis, we can consider the disproportionation of this chlorine is taking place, where chlorine is going from 0 oxidation state into -1 as well as +1 oxidation state. So HClO can still be present in this reaction medium. We cannot rule out on any of the options on the basis of the anion. We have to go back into the cations only, then only we can get some possible answer. Coming to the cations. Over here, we are having, on the basis of P, we have seen in the beginning that we can rule out all other options. Here, chromium and manganese are given. So chromium is already ruled out. We can only and only think about manganese now. And because we are being asked about Q cannot be CRO. This first option can be ruled out. Now we are left with B, C, D. And because we know that MnO-, that is permanganate, and manganate both are colored species in solution. This was supposed to be purple in color and this was supposed to be green in color. Because we were not given what color, we cannot rule out as of now from this information. We need to look into some other reactions as well. What reaction? Qualitative analysis suggested that if PbO2 in acidic medium is used to oxidize Mn2+ in acidic medium, this is known to be converted into permanganate, which is going to have purple color, something like this. So as from qualitative analysis, this option can be ruled out. MnSO4 cannot remain as such because this PbO2 is oxidizing it. This option is also ruled out. That is how we are going ahead, and we can be giving us all possible explanations why this is that, why this is not. One last thing before we move on, that is coming from the electrochemistry. We were talking in the beginning that we know PbO2, lead dioxide in acidic medium, is known to be very strong oxidizing agent. And if we have not seen that in the electrochemistry, or anywhere in the redox reactions. Actually, qualitative analysis would have been the best place where you could have seen this reaction if you have been following qualitative analysis. Otherwise, in the lead acid battery, the SRP values which we are mentioning when we are adding their electrode potentials and the cell potential, then we are mentioning these values. Those values suggest that PbO2 in acidic media is going to be very, very strong oxidizing agent. This is way stronger than permanganate. We can see their SRP values. Here we go. SRP values are suggesting that lead dioxide PbO2 as having its SRP value 1.69, where permanganate was having SRP value of 1.51. So the reactions are going to be lying in the favor of lead dioxide oxidizing Mn2 plus, converting MnO4 minus. In the sense, stronger oxidizing agent can generate weaker oxidizing agent if everything is remaining in the aqueous medium, no precipitation equilibrium going against this, no evolution of gas going against this, no change in concentration contradicting the values of the SRPs. Right? So this was the explanation why PbO2 can be oxidizing manganese into permanganate. If we don't have this enough data supporting this information, or we have not seen this ever happening in the qualitative analysis, we may be finding it, student when I interacted with them, they are finding it difficult that the PbO2 can oxidize KMnO4 because they they have this belief that KMnO4 is a very strong oxidizing agent. Indeed it is, but PbO2 is even stronger than that. And of course, fluorine is the boss of the inorganic chemistry and the boss in the terms of all the elements when it comes to oxidizing power, or power to grab the electrons from any other element. That is, fluorine is the boss. Okay, moving on, we have a small discussion about the chlorine as well. So when we are saying HCl gas in the reaction sequence, when Q was converting into the compound number Y, so chlorine, HCl gas is evolved, we know in qualitative analysis we have seen. If you react that any of the chloride from sodium chloride or any other chloride, if you react this concentrated sulfuric acid and you heat it, then HCl gas is evolved. This is in contrary to when you heat bromide or iodide. When you do so, there is bromine gas and iodine gases are evolved. Because of this is the difference how HCl cannot be oxidized very easily by concentrated sulfuric acid, because sulfuric acid concentrate is also although it is oxidizing agent, but this is not very, very strong oxidizing agent. So HCl gas is released when concentrated sulfuric acid is reacted, because concentrated sulfuric acid cannot oxidize HCl into Cl2, and it could have oxidized HBr into Br2, Hi into I2 very easily. Now when you put manganese dioxide into the solution, where concentrated sulfuric acid and chloride were already present, then not HCl, now chlorine gas starts getting evolved, which can be identified from its greenish yellow color, which is there. We can see in the image in a moment. So what we are saying, chloride ions are easily oxidized by manganese dioxide or MnOH twice in acidic medium when we are heating the solution. This is the image which is telling us here we have kept over here, we have kept manganese dioxide and we have tried adding HCl directly into this. Rather than HCl, we could have taken some chloride and say some source of H plus as dilute sulfuric acid or concentrated sulfuric acid. This we could have taken and we would have got that. So when these two things are reacting, these contents were connected over there, and then we were getting this was the exit tube which was delivering the chlorine gas over here. This was the container where chlorine gas was being collected, and you can see this color over here, that greenish yellow color is being observed in this case. Okay, but if you go for the data, there is a slight problem. The problem is SRP value of chlorine is plus 1.36, while SRP value for manganese dioxide is going to be smaller than that, plus 1.22. So why now that same thing is not working, as we have been talking earlier, that stronger oxidizing agent can generate the weaker oxidizing agent. Why now chlorine, the stronger oxidizing is, and again I want to emphasize here, more positive SRP implies more oxidizing nature. Why more oxidizing nature chlorine with more positive SRP cannot oxidize Mn+2 into MnO2? Why over here this is happening the other way around? We'll be coming to that explanation in a bit. We are going to see the explanation for all the reactions from the very much beginning, like why these reactions were giving us this kind of product. So first reaction, this was happening. The reason was precipitation reaction, because this is governed by the solubility products of these different reagents. We know that solubility product of MnCl2 is very, very high. Although this is not given anywhere, I had tried calculating this using from the data on Wikipedia, which is suggesting that the solubility of the anhydrous MnCl2 is given. So converting that into moles per liter and then converting that into 4s cube is going to give us this value for the solubility Ksp of the MnCl2. And Ksp of manganese hydroxide has been reported in a number of different places. That is turning out to be 10 raised to power minus 14. There is a huge difference in the solubility. A manganese chloride is very much soluble. Manganese hydroxide is very much insoluble. This reaction is going by the reasoning of the solubility behavior, and so we are getting the precipitation of MnOH ka whole twice. Then we are having the oxidation of manganese 2 plus taking place. That was this reaction sequence where the compound number P is getting oxidized. And here we are having two explanations possible. Number one, dissolution of precipitate is happening due to solubility of MnSO4, which is much more soluble in comparison to manganese hydroxide. And we can think about the base manganese hydroxide, acidic sulfuric acid are going to react to form salt and water, and that salt is going to be very much soluble. And later on, this MnSO4 is being oxidized from Mn+2 to +7 because the SRP value of the lead dioxide was way smaller in comparison to the SRP value. SRP values of PbO2 was higher in comparison to SRP value of manganese 2 plus. So this oxidation will be taking place quite easily. Now, the last explanation, why oxidation of chloride is taking place. This was tricky, because the reactions which were given are telling us that chloride is being converted into chlorine, and that is happening by manganese 2 plus. Although we have seen that reaction happening in the qualitative analysis, but we might not have bothered to go for the explanation about that. Here we have the explanation. We understand that those SRP values are basically for the some given concentrations. If you change the concentrations, the SRP values can be changing a little bit. We have different questions, different situations where we can make the precipitation of the like deposition of the copper and zinc both at the same time by changing the concentrations of those ions in the solution by huge extent. So change in concentration by much greater magnitude can make, although this thing possible, that may not possibly be the sole reason why chloride from HCl or from any particular source are being oxidized into chlorine. There has to be some other reason as well. We need to go back to Le Chatelier principle, where these reactions which could have been happening, the reactions that chloride being oxidized by manganese dioxide converting into chlorine gas and manganese +2 oxidation state. This chlorine gas is being evolved, MnCl2 is being aqueous, this evolution of chlorine upon being heated, there are much more chances this chlorine gas can be evolved. So this equilibrium can be shifting up to the forward direction very easily as the chlorine is continuously getting evolved from the reaction mixture. So if this equilibrium is being driven in the forward direction, what we expect? We expect chloride will continuously be converting into chlorine and MnO2 will be converting into MnCl2 during this whole reaction. Now, we have seen the similar situation as was happening with the K2Cr2O7 as well. We know from the SRP data, here it is once again, we know from this data that chlorine is going to have higher positive SRP value in comparison to potassium dichromate in acidic medium. Still, we have seen we can oxidize HCl using K2Cr2O7. If the concentration of HCl is kept very, very high, concentration of Cr2O7 is also kept very, very high, then this SRP values could be, the hurdle of this SRP values could be overcome because the overall SRPs are getting changed. The net reaction will get its that Q value changed. Rather, the Q, that is your reaction quotient value, changed when you are doing these reactions. So equilibrium being shifted, concentrations being changed, value of Q and direction of equilibrium both put together give us the explanation why chlorine gas can be evolved from oxidation of chloride by manganese dioxide, although SRP values are not in the support of this reaction. Okay. Fine. So coming back to the identification of the unknowns, these I think are we have done a lot of discussion. So this we know for the compound number P was white precipitate coming from the manganese hydroxide. Compound number Q was NaCl, and then this MnOH whole twice was oxidized. This was giving us MnO4 minus, and if you have taken the sodium in the solution, this can be sodium permanganate. If it was potassium, it could have been potassium permanganate. NaCl is going to convert into the chlorine finally, and this chlorine is going to give us blue coloration when this is reacting with the starch iodide paper. All this reaction tabulated over here once again, and this can be the overall summary of all the reactions. Here we are having the question, original question, and the option which was supposed to be true. We have to see from the options. We had ruled out other options already. We had talked about this. This is going to be the correct answer as given by the final answer key for this particular question. This is the conclusion of our this discussion. This was way longer discussion in comparison to the previous questions where we have done somewhere about 30 to 35 minutes. This has been pretty longer than that. So that is all over here in this video. Concluding here. Hope to see you in the next video. Thank you. Bye bye. Take care. And also please don't forget to consider like and subscribe this channel, which gives me motivation to do more such videos. Thank you. Bye bye. See you later.